Hello and welcome back. Let's continue the foundation engineering class. We are going to start a new chapter today, the chapter number 5. It will be about settlement of shallow foundation. Okay? But you need to understand the stress increase in ground to be able to understand this chapter. Okay? The soil mechanics, maybe soil mechanics 1, you need to know stress distribution in the ground. Okay. So anyway, I hope everyone knows about that. Everyone understand that. If you don't, please go and check my soil mechanics class. Yeah. So here is the content of this chapter. We have about 16 points. Okay. So today we will cover these two first points. So everything you can see settlement everywhere. This is because if you know only the ultimate bearing capacity of ground, knowing only the ultimate capacity of your foundation is not enough. You need to know the amount of settlement the load coming on the foundation will cause. Okay. So that is, let's say, serviceability limit state, because in some projects you will have some restriction about the amount of foundation your the amount of settlement, your foundation will cause. So you need to understand how to estimate settlement of shallow foundation. There are several methods to estimate the foundation, and the foundation also, I'm saying foundation, but it's settlement. There are several methods to estimate the settlement, the amount of settlement, and the amount of settlement depends also on the type of soil. Okay. So today we are going to cover these 2 points. First, the introduction and elastic settlement in shallow foundation on saturated clay. Okay, with Poisson ratio 0.5. So saturated clay. First, the introduction. So settlement of foundation, as I said, is different depending on the type of soil you are dealing with. Granular soil like sand, or cohesive soil like clay, and the settlement behavior is not same. Okay, so that is a very important thing. For granular soil, for example, you will see that after building your foundation on the ground, the settlement will happen immediately. Okay, it means the full settlement will happen immediately. So it doesn't take time, rapidly. This is because uh, this granular soil, like sand or gravel, they have a big amount of void that can allow the water in the ground. If there is water, that water will escape easily and faster, okay, compared to clay. Okay, so this immediate settlement is known as, of course, immediate or elastic settlement. Okay, so if you hear elastic settlement, it means that settlement happened almost immediately after loading. So it's very important to understand the definitions. And we can estimate this elastic settlement using the elastic theory. Okay? Elastic theory, don't worry, I'll come back to this again. But I think almost everyone knows about this. So in cohesive soil, this one was granular soil, but in contrary, the cohesive soil, like clay, they settlement that will happen immediately after loading is very small. Okay, the good portion, the majority of the settlement will happen over time. It will take very long time to complete. Sometimes it take years, a lot of years to complete the settlement complete. And this process is called consolidation. Okay, this consolidation is happening in soft, like fine soil, mainly, not in sand. Yeah, and it take really long time, many years sometimes. So this consolidation has two phases. Okay, the primary consolidation, which happen as the excess pore water pressure dissipate. So it means it related to how fast the water is going out from the clay soil, from the soil. Okay, so the primary consolidation is related only to the water in the ground. Okay, release of excess pore water pressure. And the secondary consolidation, that one it begins after all the water in the ground is gone, and then the soil particles start to rearrange. They start to it's like the load, the water that was helping the soil to support the load is gone. So the soil particle will receive the load now, 100% of the load. So that will make some movement in the soil particle, and this soil particle will like do some rearrangement, and that will uh, make some consolidation. Okay, so this means the soil structure will adjust because the soil will feel the load now after the water is gone. So that is secondary consolidation, primary consolidation and secondary consolidation. Okay, so as you can see, for granular soil we have elastic settlement. Okay, cohesive soil, we have elastic settlement also, but it's small. Then we have consolidation settlement, which has two phases, primary consolidation and secondary consolidation. So this means in cohesive soil, like clay, we have three type of settlement. The settlement that occurs immediately after loading, which is elastic settlement. Okay, it was here for the granular. Okay, elastic settlement, primary consolidation, secondary consolidation. For cohesive soil, three types of settlement. But for granular soil, we have only the elastic one. Okay, and the elastic one in the cohesive soil is really small portion. So let's now try to talk about primary and secondary consolidation. Actually, this introduction is normally everyone knows about this from the soil mechanics one. So a significance of each of these phase depend on type of soil. Okay, so if you go in the uh, cohesive soil as well, these primary and secondary consolidation, they are happening differently depending on the type of cohesive soil. Okay, if you take for example an organic clay or silty soil, the primary consolidation is typically dominant. Okay, it means the secondary consolidation is almost not, it doesn't exist almost. If you go to organic soil, the secondary consolidation is significant. If they, for example, if you take peat, okay, after all the water is gone, The secondary consolidation, which consists of rearrangement of the soil particle, will be really big because pit cannot support load at all easily. So it will really shrink, the soil will shrink down. Okay. So even within the cohesive soil, the primary and secondary consolidation are not safe. Okay. So in this chapter, we'll try to introduce the main theory. The theories used to estimate both elastic settlement and consolidation settlement. Okay. Elastic settlement, which happen fast, immediately after loading, and the consolidation, which take much longer time. Okay. And remember, consolidation, we have two types. So we are going to see how to estimate these. Okay. So when you calculate elastic settlement, the one that happened first, you need two key parameters. The modulus of elasticity, okay, which is also related to Young modulus. Okay. For soil, this can range from 1 to 50 megapascal. And this soil parameter is obtained mainly from in situ testing, the site investigation. We talked about this in chapter number 2. Please go back and see the lesson in chapter number 2. Yeah. And the portion ratio, that also can be obtained from a investigation, but it normally range between 0.0 to 0.5. People use 0.3 usually. It depends if you are dealing with sand or clay. Sometimes 0.5 for clay. Yeah. So you need these two parameters in case of elastic settlement, the settlement that happen immediately after loading. For that, you need these two key parameters, okay? The elasticity modulus and Poisson ratio. Sometimes the Poisson ratio, the symbol is like not like this, okay? It's like sometimes like V, S, okay? Anyway, for saturated clay, for example, under undrained load, water is not drained. For saturated clay, under undrained load, where we have volume change almost not existing, the elastic theory shows that Poisson ratio is typically around 0.5. That's why I said for saturated clay, okay, just take 0.5 for Poisson ratio. Okay, I think that will be okay enough for the introduction. Let's go now for the elastic settlement of shallow foundation on saturated clay. And we just said that for saturated clay, under any condition, we can take Poisson ratio 0.5. Okay. So elastic settlement, the one that happened immediately after loading. How do we calculate it? As you know, we need the elastic modulus and the Poisson ratio. Yeah. And this is for clay. And remember that for clay, the elastic settlement is very small. Okay. So we have an equation that is proposed to to evaluate average settlement of foundation on saturated clay, given like this. We have this equation, okay? A1, A2, K0, B, ES. You already know what is ES, I think. B also. B is just the dimension of your foundation, okay? Supposing you have this, the width of the foundation. If you are dealing with circular footing, then B is diameter of your foundation. Okay. So means we need A1, A2, Q0, BES to obtain everything. About A1, Okay, this is not giving directly A1, but it give you information telling you that A1 is function of the embedment ratio and is L bar B. We will see what is this soon. Okay. So for A2, A2 is a function of the embedment ratio. Sorry, I said this one is embedment ratio. It is not embedment ratio. H bar B, H, you can see H here. See this. And B is the dimension of the footing. Okay. So D embedment, yeah, this is the embedment ratio. So H here is like the soil. This layer is like a rock, like non-compressible layer. So it is not the or not the clay. Okay, the clay, another soil. The clay is the thickness of the clay layer. Okay, because we want to deal with a the settlement of saturated clay. Okay, so H is then the thickness from the base of the foundation of the clay layer. So L is the length of the foundation. If you are dealing with, for example, square footing, L and B are the same. Okay, so we need L bar B here to estimate A1. B, you know it already, width of the foundation. DF, the embedment depth of the foundation. H is depth of the bottom of the foundation to the rigid layer. Okay, from the bottom of the foundation to, as I said, this layer is like rock, like not easily deformable, rigid layer. Okay, so this is the clay. H is the thickness of the clay from the base of the foundation. Okay, and K0 is the net